This is Sara Hojjatie, Lab Section M04, presenting Lab 5, Motion of Falling Objects. In this lab, the motion of two objects was observed, one heavy object with a small surface area, which was a bag of Godiva chocolates, and one small lightweight object with a larger surface area, which was a yellow folded paper. The main objective of this lab was to observe the effects of gravity and drag on two objects and compare the differences in the amount of drag for each object, ultimately seeing if the objects reach a terminal velocity. So as you can see right here, I videotaped myself dropping a bag of chocolates and set my axis so that the chocolates fell in the negative x direction. I calibrated my length scale by setting the length of the chocolates to be 0.245 meters. The beginning point of my observation is at frame 6 and my end point is at frame 18. I set the initial position of my object to be at the origin and it was oriented lengthwise across the x-axis. The final position of the chocolates was at negative 0.73. The time length of my video was from 0 to 0.4 seconds. I took this data and created a computational model in VPython. My start time was 0 and my time step was 0.033 because that was the time step used in Tracker. My initial position was at the origin because that's where I decided to place the origin. My initial velocity was 0 because my object began at rest. The mass of my object was found to be 0.198 kilograms. Now on to the while loop. I set the force of gravity to be equal to negative mg, which is the mass multiplied by the gravitational constant, which is 9.81. That will be in the negative y direction as specified in the comment. In the simulation, we wanted to see the predicted motion with only the effect of gravity, so my net force was set to be the force of gravity. I then plugged into the velocity update formula the force divided by mass as the acceleration, since F is equal to ma. After the program was run, the data was exported into an Excel spreadsheet, plotted and compared to the actual data. Here you can see the actual and the predicted data points match pretty well at the beginning, but the points deviate towards the end. Next, I tried to see if I could get a better predicted fit by adding drag to the VPython code. The formula for drag proved to be from our lab assignment, and it was the drag constant times the magnitude of velocity times the negative direction of the velocity, which can be simplified to the negative drag constant times the velocity. This equation was used and the net force was updated to be the force of gravity plus the force of drag, which is in the opposite direction. Then I had to experiment with different b values to find the drag that has the output of the position and the time that matches my actual position and time. I found that to be at b equals 0.16. So I exported this data from VPython to Excel and plotted it with the actual points and found the curve to be much more fitting, especially towards the end of the graph. The predicted path still deviates slightly in the middle of the points, which is probably attributed to some error. Now I did the same thing with my light object, the yellow folded paper, right here. I calibrated the length of my paper to be 0.158 meters. My initial time was 0 and my final time was 0.47. My initial position was at the origin and my final position was at negative 0.46. I began at frame 15 and ended at frame 29. I made my object begin at the origin and changed my axis so that the object fell in the negative x direction. I exported my tracker position and time data into an Excel spreadsheet. Next, I created a computational model in Tracker with my initial conditions exactly as with the previous object. However, the mass was much smaller. It was 0.005645 kilograms. For the force, the initial computational model only deals with gravitational force. So it is the same as with the previous object as well. However, in this case, the final time is 0.47 because the object fell for a longer period of time. As you can see with the predicted motion with just gravity, right here, it is a terrible representation of the actual data. Next, I took into account the drag force and added it to my computational model. In this case, my b value was 0.042, which was much smaller than my previous b value of 0.16. Now, when I exported this data into Excel and graphed it with my actual data, it shows a much better fit to the actual data and almost fits perfectly, as you can see right here. As you can see, the paper does reach terminal velocity after about 0.15 seconds because the magnitude of the drag is equal to the magnitude of the gravity. Now for the what does it mean question, we had to compare the predicted motion for the effect of just gravity and gravity plus drag force on the light object and see which one predicts a terminal velocity. Basically, our net force is equal to the sum of the gravitational force and the drag force, which are in opposite directions. If the magnitude of the gravitational force and the drag force are equal, then our net force is 0, and thus our acceleration is 0 because F is equal to ma. This means that we have a constant velocity, which is represented by a linear trend in the position versus time graph, meaning that the object has reached terminal velocity. The heavier object does not reach terminal velocity because there is a very small drag acting upon the object. However, for the smaller object, terminal velocity is reached because there is a large drag force acting upon the object, with a magnitude almost equal to the magnitude of the gravitational force. If there was no drag, the object would just keep increasing speed at an increasing acceleration, which can be seen in the graph to the left, right here. We've moved on to our what if question. Due to the effect of drag, the object slows down until it reaches its terminal velocity, and then continues to move at a constant velocity of its terminal velocity, as can be seen in the right graph. So this pertains to the what if question, asking if we drop the object with an initial velocity of anything, in this case -4. So the light object would reach a terminal velocity sooner with drag, but without drag, the light object would continue to increase in acceleration, which was just explained. So in conclusion, terminal velocity is achieved only by the slowly dropping object.